We're going to look at the algebra of functions, sum, difference, product, and quotient of two functions. So in other words, we're going to add two functions together. Here's our notation, f plus g, could be just the function names. F plus g in parentheses of x, or f of x plus g of x. This is the one I like to use primarily. I will shortcut to here. But sometimes if you're not using FG's and H's, you don't think you're using a function, so I like to have the f of x there. The difference function, we're just subtracting two functions. You probably want to circle this right here and say, remember, distribute the minus sign. Product, we're going to multiply two functions together, so you might want to put above here foiling, distributive properties. Quotient, we're going to be dividing two functions, so as soon as you put a function in a denominator, remember that denominator function, g of x, can never be equal to 0, so you have to go find that disclaimer. So let's look at some examples here. F of x is going to be x squared plus 9. G of x is going to equal 3x plus 5. Because they're both polynomials, both functions have all real numbers. There's no restriction on their domain. So if I wanted to find the f function, we'll let this one will be work in blue. The g function will be the work in red. So if we want to do f plus g of 2, I'm going to think of f of 2 plus g of 2. I'm going to put 2 into the f function, so 2 squared plus 9. In its own separate brackets. I like to keep brackets here because it helps when we get to foiling and when we're dividing so you don't cancel anything. And then we'll put the 2 in for the x of the g function, 3 times 2 plus 5, so we're going to get 4 plus 9 in the blue brackets, 6 plus 5 in the red brackets. 4 plus 9 is 13, 6 plus 5 is 11. So what's actually happening here is you're using the x coordinate of 2, but with the f function, it gives you a y coordinate of 13, and the g function's y coordinate will be 11, so we're just adding the two y coordinates together to come up with 24. So f plus g of 2 is 24. It's a whole new function, the new point 2 comma 24. If we want to do f minus g of 5, same concept. I'm going to take the 5, substitute it into the f function, keep it in blue brackets, take the 5, put it in for the x of the g function, and again, keep that in red, and simplify each one of these individually, and the last thing I want to do is to subtract. So 5 squared will be 25, 3 times 5 will be 15, 25 plus 9 is 34, 15 plus 5 is 20. The last thing we do is subtract these two y coordinates, and we get 14 for an answer. F times g of negative 2, again, negative 2 is going to go into the x of the f function, and of the g function, keep brackets there. We want to simplify each function individually till at the very end we multiply. Negative 2 squared will be 4. 3 times negative 2 will be negative 6. We'll have 13 times the negative 1, which is just negative 13. Keeping my same functions here, f divided by g of 1. We'll put f of 1 on the top, g of 1 on the bottom. And the first thing I would do here is I would mentally take the 1 and put it into the g function because this is the denominator. If this becomes a 0, it doesn't matter what we have up here, it's undefined. So it looks like 3 times 1 is 3 plus 5 is 8, so that's okay, we'll plug it in. We'll get 1 plus 9 is 10 over our 8, which reduces to 5/4. Now, f plus g of x, they don't give us a number, so now we got to keep everything in like terms. So f of x is the x squared plus 9, g of x is the 3x plus 5. We're going to add them, so we don't need the brackets. Again, I use those to set it up. The only like terms we have are 9 and 5, which will become 14, so my final answer is x squared plus 3x plus 14. If this is an x here, then you have to have x's here. If you have a value, then you end up with a value. fg minus f of x. Again, subtraction. Remember I told you in mental note we have to distribute the negative. So this minus sign has to distribute to both terms, which makes this minus x squared minus 9. Combine like terms, 5 minus 9 will be negative 4. So negative x squared plus your 3x minus 4 in descending order is my answer. F of x times g of x. Here we're going to take these two binomial functions and we're going to FOIL it. X squared times 3x will be 3x squared. X squared times 5 will be 5x squared. 9 times 3x, 27x. 9 times 5, 45. No like terms to combine. That's our final answer. Divide f of x divided by g of x. So x squared plus 9 goes on the top. 3x plus 5 goes on the bottom. You think that would be the final answer, but it's not. Remember what we declared at the very beginning. Polynomial function, their domain is all real numbers. Because we put 3x plus 5 in the denominator, we have to go solve it for x by setting it not equal to 0 to make sure that we can't have a negative 5/3. Subtract the 5, divide by 3. So you have to add this to your answer. Now, what I don't like about your homework is that they obviously want to write small amounts of computer code. So they'll ask you for what is f of x divided by g of x. They'll put this answer in. Then they'll have a follow-up question. What is the domain of f of x over g of x? Okay, so this is the implied domain, all real numbers except x can't equal negative 5/3, or you have to use your interval notation, negative infinity to negative 5/3, open interval, parentheses, union, parentheses, negative 5/3 to infinity. You answer it as two separate parts, but in reality, this is the function, and you attach the domain restriction with it. So we have g of x over f of x, so 3x plus 5 now on the top, x squared plus 9 on the bottom. So here's my answer again. Take the denominator, setting it not equal to 0. If I think about subtracting over the 9, x squared has to equal a positive number. There's no way it can equal a negative, so therefore it's not possible. This has no domain restriction. There's no way to get 0 in the denominator, so we don't have to worry about a domain restriction. Now, the next problem, remember our previous example started with all real numbers. Now we start with restrictions. So now you could run into multiple domain restrictions. So first things first, j of x is 1 over x plus 2. We can clearly see that in the denominator, x cannot be equal to a negative 2. Declare that. In the k function, x minus 1, x cannot be equal to a positive 1. Declare that. Whatever you do with these two functions, these two domain restrictions must be attached to your answers. There are no other possibilities. If I add these together, these two domain restrictions are there. If I subtract the two, the domain restrictions are there. If I multiply the two, the domain restrictions are there. If I divide, you might come up with another number. All right, so j divided by k of x. J of x over k of x. This can get ugly, so bear with me here. It's going to be 1 over x plus 2 in the numerator and x over x minus 1 in the denominator. This is that complex fractions that we saw from section 6.5. Remember, one fraction on the top, one on the bottom. All right, rewrite this as division. We're going to do that type 1 technique. There it is as a division. Now think about multiplying by its reciprocal. So x minus 1 over x, we multiply that together, x minus 1 over x times x plus 2. Now wait a minute, there's a new factor in your denominator. There's an x down here. So now we have to add, x can't be equal to 0, with these two existing restrictions. Now, I know what you're thinking. Well, why can't we take away the 1? Because the 1 is now, x minus 1 is up in the numerator. Doesn't matter. It started in a denominator. So if you think about this, why are there 3 restrictions? 1 denominator, 2 denominators, and then this whole entire x over x minus 1 is in a denominator. So this x in the numerator would be a 0, makes the whole big denominator 0. And that's why there's going to be 3 restrictions. That will be a trick question, guaranteed. You'll see that in the future. All right, adding and subtracting functions using graphs. So pay close attention here because I always get people confused here. What is the domain of r of x? Everybody can answer this one. Oh, we go to the far left x all the way to the far right x. So we're going from negative 14 all the way over to 4. There's my domain in a compound inequality. And then interval notation, bracket, negative 14, comma 4. S of x, that's the blue function here. Far left x, negative 9. Far right x, it's going to be 11. So negative 9 less than or equal to x less than or equal to 11, or interval notation, negative 9, comma 11, with brackets around both sides. Now, here's where the confusion comes in. Find the domain for when you add these 2 functions, subtract these 2 functions, and multiply these 2 functions. Notice division isn't here because you saw in the previous example that you might create more restrictions. So I'm isolating that one for the next slide. So add, subtract, multiply. Now think about what we did earlier. Remember when I said when we were adding, you're really adding the 2 y coordinates, subtracting the 2 y coordinates, multiplying the 2 y coordinates. So if I wanted to be able to add these 2 together, I would have to be able to find a y coordinate in the red and a blue y coordinate so I can add them together. So it would be really hard to have this point, which is at negative 11, for my x, because there's no point for x equals a negative 11 for the blue graph. There's nothing to be able to add together. Or vice versa, if I'm way over here, and here's the point 8 on the blue graph, 8, 0, and I want to find a point on the red graph for x equals 8, there's no point, then there's no y coordinates to add. So if you look at this really closely, in order to find a domain here, these 2 graphs are going to have to overlap. I'm going to have to take the smallest of the 2 left endpoints, or I shouldn't say the smallest, the largest of the 2 left endpoints, and the smallest of the 2 right endpoints. I have to have where the graph overlaps. This is the new domain. Negative 9 less than or equal to x less than or equal to 4, or an interval notation, bracket negative 9 comma 4 bracket. All right, so it's where it overlaps. Now, I did have a student ask me one time, said, hey, Mr. Fitz, I got a question. Can I do the following? I see a pattern. Can I put my x's in my compound or interval notation in numerical order and then just grab the 2 middle terms? I said, that works fine as long as what happens? They have to overlap. I said, what happens if you had, negative 14 less than or equal to x is less than or equal to 4, and then this one started out 9 less than or equal to x is less than or equal to 11, and you got 4 and 9 here and nothing overlaps, you can't grab the 2 middle numbers. So they have to overlap in order for you to add these together. That's the domain. All right, overlap, 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 overlap. Keep saying it to yourself. Now, let's look at division, because division gets a little different. So if we put s of x in the denominator, that means s of x cannot be equal to 0. That means s of x cannot be equal to 0 for a y-coordinate, which means it's going to cross the x-axis somewhere. So what we're going to do is we're going to look at our overlapping domain. We're going to go -9 to 4. And we do have 2 x-intercepts, but only one of them is in between our overlapping graphs. So we don't have to worry about this one. This 8 doesn't fall in my domain from -9 to 4. But this -2 does. So my domain is still the bracket -9, 4 bracket. You just attach that individual domain restriction. Now, if the homework wants this all in interval notation, then we go bracket -9, -2 parentheses, union parentheses -2, 4 bracket. Either one is acceptable for me on the test. Everybody agree. Take a deep breath. I need the overlapping area region no matter what. Then who's ever in the denominator, I'm looking for an x-intercept. Now, if we switch this around, let's say we go s of x over r of x. I'm still overlapping. But look at my r of x graph. Does it cross the x-axis? No, it doesn't cross the x-axis anywhere. So then there's no restrictions to worry about. It's still the overlapping domain, bracket -9, 4 bracket. All right. Okay, let's put some numbers in. Let's say we want to do r plus s of 0. R of 0 plus s of 0. Okay, that's between -9 and 4. It's all good. All right, here we go. We go to 0. I go up to the r graph. Uh-oh. It's not hitting the tick mark perfectly. The blue graph, oh, that's a 2. I got it. Now, the question is, how did I know that this was 5.6? Okay, I'll tell you how I knew that. This is a line segment which has a slope, and its slope is down 2 and to the right 5. So down 2, right 5 is -2/5, or as a decimal, -0.4. So at this point right here at -1, I'm at 1, 2, 3, 4, 5, 6. So from 6, I go 1 squared to the right. I have to go down 0.4. So 6 minus 0.4 is the 5.6. So every time your x goes to the right one, you go down 0.4. So this would be 5.6, 5.2, 4.8, 4.4, and a 4. So that's how I knew this was 5.6. I did not guess. I worked it out logically by looking at the slope of that line segment. So 5.6 plus 2, 7.6 is my value. All right, r of s, or excuse me, r minus s of -7. So r of -7 minus s of -7, that's between -9 and 4, so we'll go to 7. -7 right here, so up 1, 2, 3, 4. So this will be a 4. Then down 1, 2, 3, 4. Down -4, so minus a -4 changes to plus plus. So 4 plus 4 is an 8. So you can literally say there is a difference of 8 squares between those two. All right, r of s, or excuse me, r times s of -4. So r of -4, find that y-coordinate, find the y-coordinate for s of -4, multiply the two together. -4, 1, 2, 3, 4, we're right here. I go up to the right graph, I'm at -4, 5. Okay, so this value is a 5. I go down 1, 2, right there, I'm at -2. Put in the -2, multiply the 5 and the -2, multiply those y-coordinates together, we get -10. And that's how we handle these graphs. And that concludes 7.4.